Hey there! So this is going to be a review on the Rigaku NEXDE XRF spectrometer. So you're not really going to find many people with these machines, and for a very specific reason why. They're pretty damn expensive. I'm not going to go into the details, but these similar type of machines typically cost around $60,000 to $70,000. So yeah, even used, like we've been searching for months, and even used, like a 10-year-old machine, their older model, they go for like $20,000, and that's like as is condition, no guarantee, no nothing. You know, if you get it and don't work, then it sucks for you, sort of deal. Yeah, for 20 grand. So we've just been searching so long. We purchased a Chinese XRF machine, and that one just had, it basically didn't work at all. And after tariffs and everything, we spent like $16,000 to $17,000 for that. That was a huge scam. I'll make a video about that. But anyways, we searched around for our applications. We decided that this is the best machine available. So some summaries reviews about this machine. So pretty much it was called a energy dispersive XRF system. They have their CG, NEXCG2, and that's called a Cartesian geometry XRF. And pretty much how that one works is that you first have an X-ray hit a material. That material will illuminate its own X-ray source at a very specific spectrum. Okay, and then that very specific spectrum hits your material, and then that material illuminates its own X-rays and so forth. The point is, the benefit of the CG versus this series is the CG has less of the background curve that this one would, because that it hits that secondary source that illuminates its own spectrum at a very specific, you know, frequency. You don't have that curve that will pretty much cause some issues. But we've decided that that machine was really good for us, because this machine, you're able to remove the sample tray, and you have this huge area you can put a material in, like bars, coins, so forth, and directly on the measurement device. And yes, you know, we decided for our application that was a lot better. And that Cartesian geometry, that secondary reflection sort of thing, that's really a lot better for lighter elements. So, you know, again, in our application, we just decided that this machine was more sufficient, and the other machine was like another, I think, $15,000 or $20,000 more expensive. So, you know, just cost analysis benefit, we decided that this machine was a lot better, and we'll put that extra money into the wavelength dispersive XRF. We have a Rigaku Primus 2 that we're trying to fix up and work on, but that'll be another video. Anyways, let me focus on this machine, its capabilities, its applications, and how to use it, so on and so forth, and what we'll be using it for. So this is the machine. We bought it with the computer set. The computer set was another like $2 grand, but we decided just to, you know, for such an expensive machine, we'll just pay upfront for the computer instead of, you know, trying to risk buying our own computer, and, you know, has whatever compatibility issues, so on and so forth. But yeah, so again, this is a what's called a direct excitation. So this just has a it has the X-ray source that hits your target, and then after it hits the target, it goes down. It has 3 different crystal filters that it'll filter. I'll show that here in a second. But after it passes by the filter, it goes into the detector. It has a silicon drift detector, which is considered one of the best detectors that you can get. So yeah, as you see, this tray is very easy to take off and put on. You just have this knob, take it off, and then you just kind of align it plus or minus, and then rotate it until it just drops into place, and just very lightly tighten it. You don't want to tighten it too hard. They came in with these little cups. I really like these cups. They're kind of fun to assemble. But yeah, they're a 3-piece design. So as you see here, and pretty much how it works is you first get some plastic film. Okay, you cut out a section on the cup. On the big, this is the ring, so you have a ring, and then you have this inside cup. Technically, you don't want to touch the centerpiece where you'll be measuring. This inside cup actually has a ridge on the top, and the bottom part is a little, like, it's kind of cone shaped, and pretty much you aim it downwards and just push it down. You also want to do this on a piece of fabric or something. You don't want to do it on a flat surface, because what will end up happening is air will get trapped in and it can actually bust this. I'll break this open, but yeah, as you see, it's perfectly clear. Very, very nice sample cup to measure. And they also have a lid if you're doing liquids and stuff, and just in general it's good to have this. That way you don't have material escaping and, you know, contaminating the system. So very good to do that. There's an entire training course that they go through you when you purchase the machine. So, you know, I'm not going to go too much into details about that. But yeah, let's actually look into the machine and how it measures, how it operates, and so forth. So this is the Rigaku FP applications. So in short, how XRF machines typically are utilized is, let's say you buy most XRF machines, they don't really have anything in there that will allow you to measure anything. Maybe very basic features. But pretty much, let's say you buy an XRF from most companies, you want to measure this cup that has, for example, ore inside of it, liquid inside of it, whatever. You will have to send that material to a laboratory and do what's called the ICP mass spectrometer spectroscopy. Anyway, sorry. The point I'm trying to get at is you're gonna have to send it to a laboratory where they use this different machine to pretty much manually analyze and calculate every single thing inside the sample, and it's a very, very difficult and extensive process. But what ends up happening is you create what's called a standard. Okay, that standard is again, it's a standard. It's a measurement that you know in 100% with accuracy what's inside of there, and you use the XRF to go based off that. So for example, let's say again I have this ore. So you have two ways. Like I said, you can send this ore to an ICP lab so that they give you a standard, or you can purchase, if you know what this type of ore is, you can purchase from already existing labs. There's even some that are federally run by the United States government and so forth, with already known standards, and they'll just provide you of a similar type of ore, and that way you can put that data into your XRF machine. It knows exactly what is in that standard, and when it measures the material that you're trying to measure that's similar to that, is able to calculate the difference in the spectrum and tell you what's inside of that ore, if that makes sense. So that is typically how most XRF machines measure, again, with most companies. Now Rigaku, and there's a couple other ones, but they have a very great software. This is called the Quant Easy FP software. But pretty much what you need to know, fundamental RPF SQX fundamental parameters software. And with this software, you're pretty much able to create your own mixtures of what you know is or what you think could be in that material, and then it'll do a calculation, its own calculations based off every single element on the periodic table, or again whichever elements you select, and also depending on the material type. So again, so you can either have solid metal, you can have oxides, so ore, for example, powders, you can have liquids, or even polymers. And in the software, again, you tell it what kind of liquid it is or what kind of polymer it is, and it'll do a calculation based off that. So, you know, or you can even have scattering FP. Let's say you have some sort of soils, or you don't know. So what it means by balance is, let's say you have organic materials, but you don't know, for example, a great example I was provided was with antifreeze. So you don't know, for example, what kind of antifreeze is in that in the car in the solution that you're measuring. You don't know if it's polyglycol or, you know, something else. There's many different types of antifreeze. You don't know in what concentration it is. You don't know if it's at 25% concentration, at 75% concentration, right? So on and so forth. Point is that let's say you don't know exactly what is in that mixture, then you could go with scattering FP, and it uses different calculations to give you a different answer. So that's what we really liked about the Rigaku system, and why one of the reasons why we chose it. So yeah, let me show you the software and running it. So we'll do for example a analysis. So here we have the analysis that we want to do, and this is called the easy analysis. So I've already set up some applications, and in this case, for example, here, let's completely close this out. Let's do another easy analysis. And then, for example, on chamber number 2, I like to not put anything on chamber number 1, because when the machine is finished, that's where it resets to. And if you ever have this plastic break or whatever, it'll drop down on the sensor. So I just never keep anything on position number 1. So on position number 2, for example, we'll go here. We'll do powder, and then, for example, if we click on start here, it'll tell us to close the door. So we'll close the door, click on OK again, and now it's going to give this a couple times. There you go. Okay, so now it's running the software. It's gonna take some time, and that is another downside of XRF measuring, but it's very, very useful. So again, to explain what the machine's going to do right now, it's going to run 3 different tests, and it runs them at 100 seconds each. Again, in the software, when you do that, it's very easy to set it up, and you can change how long you want to do, what conditions you want to do, if you want to do in vacuum, if you want to do in air, if you want to do in helium purge, so on and so forth. But in this case, I'm just doing air. And what it does is, again, it emits an X-ray at a certain voltage, and it has a certain filter that it filters out the X-ray with. Okay, and it does that at 3 different stages. It actually changes the voltages. So right now it's running at 60 kilovolts, and then, you know, doing the F filter. So it has 3 different filters and 3 different voltages it runs at, and it does 3 different tests. Again, this is what makes this rotary table very nice. You can just put in 10 different samples or whatever, 15 different samples, leave it and run it overnight or whatever, because, you know, at 10 samples it'll take over an hour, almost 2 hours to run. So yeah, it's very, very, very useful to have that rotary table. That way you're able to work on other stuff. So I'll cut this video, and then let's skip forward to when it's completed. So once we got our measurement done, we can have 2 options we can do. Firstly is spectrum display, and then quant calculation. So I always like to do just quant calculation first, figure out what exactly is going on. So here's the actual full measurements. Then what I typically like to do is output, order by analysis value. You can also even change the units here. So right now it's just doing milligrams per kilogram. We can also do like ounces per ton, so on and so forth. There's many different options. So yeah, as we see, it gives us our measurements. So if we see here, for example, we see this is mostly zinc and lead ore. It's sulfur. It has sulfur, and obviously it has calcium silicon, as typical rock steel, so on and so forth. Basic things that it's showing. But what's really interesting is this. So it's showing us iridium it has in. And then also platinum and gold, but whenever you see that parentheses, the commas, that means it's within the margin of error. So if you see the margin of error here, and it does all this calculation by itself, and I'll show you what I mean, or why it says this. But yeah, pretty much it shows you the it's calculated margin of error. And yeah, so again, I would never go based off any of these results immediately, blindly, based off themselves. Especially with the lower ones, what I would then do is, for example, iridium. Okay, so I'll show you an example of iridium, platinum, and gold. So firstly, we'll look at what exactly is the elemental line. So it's looking at the IR, the LA lines, and same thing with the gold and platinum. So look at the LA lines. But anyways, once we know that, we do closed quant calculations. We go to spectrum display, and it'll ask us the 3 options. We'll just open them all. Hold on, let me minimize this. So there you go. So now we have our 3 spectrums. Okay, and remember I was talking about earlier about how it uses 3 different filters and at 3 different voltages to measure. Well, this is exactly what I'm talking about. So we want to find our LA line. So here we see the gold LA lines, and if I'm correct, I see iridium, gold here. There should be also a platinum one somewhere here. But anyways, let's open this up and see. So where is it? There you go, platinum and AU gold. So this right here is where it's calculating the gold and platinum at. So if we zoom into here, we can see the problem that we're facing. So we have this huge zinc curve. Remember earlier I was saying we have lots of zinc, and whenever you see zinc, pretty much as you use your XRF machine, you'll just become familiar with this. You'll see, okay, if there's zinc in this material and it's showing possibly gold and platinum, I know I need to be careful with that, and here's why. So the zinc curve, as you see, it's a very, very, very big hill, and the gold measurement is right here, and the platinum measurement is right here. And because of that, what that's causing is that it's two things. Either there's no gold, there's no platinum in this material, and it's just calculating the zinc curve as part of that. Or secondly, there is platinum, there is gold at a very small amount, but it's being covered up by the zinc curve. So it's very difficult to say. So what you do, what I like to think of an XRF spectrometer as, is this dance, that you go back and forth with the data. So now that we see this, now that we know this, okay, here's what we'll do next. We'll do acid refinement or other chemical refinements to remove that zinc, right? So we'll use just, for example, hydrochloric acid or whatever to remove that zinc, or we'll desulfonate the ore first and then measure again. So you pretty much dance back and forth with the data to remove that zinc, for example, and then measure again. And if you see that the platinum and gold levels went up, then boom, your ore has platinum and gold. Again, let's go with iridium, for example. So iridium typically is around lead. So right here, lead. So again, if we do the measurements, so the IR, what was the IR LA lines? Yep, right here. So IR LA lines. So again, if we go here, measurements. So again, we have the lead curve, but again, as you see that they're so right next to each other, the lead and the iridium, that is very difficult for the machine to be able to, at least I believe, again, the machine says with confidence that there's iridium. We're not sure with 100% guarantee. So we're how do I say this? The best, again, the best explanation I got during the tutorial was, I wouldn't bet all your money on this that this has iridium, right? But this is a very good sign. It's a very good indicator that we can start taking the next steps forward. So XRF spectrometry will never be able to tell you what it doesn't have, but it can tell you if it does have something. So what we can now do is, again, since we know that there's a possibility that there's iridium, we can do acetic acid, so vinegar, to dissolve that lead, in order to check and again do measurements again after the chemical measurements, the chemical dissolving of the lead, to measure the ore again and see if it has iridium. So that's an example of how you can. And also another great thing about this software is you can actually save this data, set it as a I think, what was it called? Set it as a reference spectrum. Okay, you set it as a reference spectrum, and then afterwards, with the next data that you measure, you can actually have the software compare the two and tell you the difference between the two of the elemental changes. So, again, this software is very, very, very useful, and doing that and actually seeing what you're able to do. The problem with a lot of handheld XRFs is, first of all, they're only able to measure maybe a dozen or two at most elements at once. They have very specific software programs that do assumptions and calculations of what's already in this ore and already in the material that you're measuring, and that's not going to be, at the end of the day, always guaranteed what you're actually working with, especially when you're doing research, especially when you're doing experiments. And in our case, that's also the second thing that we need this XRF for. So right, again, the first thing that we needed is the a very accurate XRF machine. The second thing that we needed is something that can measure liquids and metal powders. So the reason why for us that's very beneficial is because when we're doing the acid leaching, we want to measure the solution before we leach the solution. We measure that into the XRF machine, set that as our reference data, right? And then we measure it again after or while we're leaching the solution, measure it again and see if there's any gold dissolved, if there's any platinum group metals dissolved, if there's any rare earth elements dissolved, right? So on and so forth. And that allows us to do comparison and sets standards of what we need, and what we're changing, and how what we're doing is affecting the changes. So, again, we can measure the ore beforehand, we can measure the ore after leaching and see what difference it has. And same thing with the powder. When we electrolyze it, we can measure the powder, see what's inside of there, do chemical steps, refining steps to change that powder, and see what changes in our steps. And pretty much our goal with this entire project is to create a completely open source mining technology where we use saltwater and electricity, or saltwater based electricity chemicals, hydrochloric acid, sodium chloride. Both of those are made using saltwater and electricity, and create this eco-friendly, very high efficiently, very economical way to completely extract all the platinum group metals, all the heavy elements, all this toxic stuff in that ore, and output it into this concentrate powder, and then further open source technology on how to further separate and refine each of those elements. So again, I hope you can understand how expensive this project is becoming. We're actually also in the process of building a new facility. That's the reason why I haven't really been uploading at all this past month. I've just been focused on that new facility that we're constructing. So yeah, some big changes are going to come up soon. If anyone's willing to help out, please help out. This is a project for humanity. This is a project for everybody. A lot of companies are going to make a lot of money based off this technology. My goal with this isn't to get rich or anything. My goal with this is just to see the end results of this, and see how the end product of this will result in great innovation and change for technology. So yeah, there's a lot of other things I'd like to do. I'd like to make redox flow batteries. I'd like to make vertical takeoff aircraft. So this is just a stepping stone into all that. So if you like this video, subscribe. There's a lot of other stuff I'll be doing, and if you're interested in XRF, reach out to me. There's I can help out as much as I can, but there's just so much options, so much research I did into all this, and so far the best option we found was this. Our other model XRFs, I think it's like a Bruker or whatever. There's just many different XRF options. A lot of them are, like, for example, for specialty applications. A lot of them are especially used for like measuring the thicknesses of, let's say, on PCB boards, measuring contaminants on PCB boards, so on and so forth. So in our application, that wasn't really needed. That doesn't help us on our applications. We really needed something that is a lot more flexible, and mostly for unknown applications where we're unfamiliar with or unknown what the sample is, what it composes of, and then with the software we're able to measure and do steps and trying to figure out what it has. So yeah, again, thank you for watching. Hope you like this video, and yeah, stay subscribed for some huge updates pretty soon.